All right, we are moving into chapter 2. This is our third chapter that we are in with College Algebra, and it's going to be a little bit more of some graphing coming into play here and some function analysis and such. So section 2.1 is devoted to the basics of functions and their graphs. So in section 1.1, we looked at graphing ordered pairs on a coordinate plane. So if you remember, we had the x's going left or right and the y's going up and down. So let's expand this idea into the concepts of functions. So because it is kind of our first section in chapter 2, we're going to get a little bit more terms in this section than what we normally do. So our first one here is a set of ordered pairs is called a relation. A set of ordered pairs is what we call a relation. And the set of all allowable x's, so maybe I should remind ourselves for ordered pairs, we have an x comma y. If I just look at all the x's, that's what I refer to as the domain of our relation. And the set of all y's is what we call the range of the relation. Okay, and so those terms are going to be very, very important here when we start talking functions. Now, much of higher mathematics involves functions. And what a function is a correspondence from the domain, which if you recall just above are our x's, to the range, which is our y's, such that each element in the domain corresponds to exactly one element in the range. And in other words, no two ordered pairs have the same x's and different y's. Okay, so I can only have one x going to one y. I could have another x going to the same y, but I can't have two x's going to the same y, or excuse me, two x's going to two different y values. Okay, so if we have these relations here, these are just relations in set notation where I have a group of ordered pairs. We want to determine whether each relation is a function and determine what is the domain and the range. So let's do the domain and range first because it's actually the easiest. The domain are our x's and our range are our y's. So I'm going to, in set notation, I'm going to pick all the x values. So 1, 3, and 5. Since 5 is repeated, we're not going to write it twice. Then we have 2, 4, 6, and 8. Looks like some even numbers as our range. And so now we need to determine if we have a function. Again, one y value has to only go to one x value can only go to one y value. So here, 1 is the only one that I have. 3 is the only 3 that I have in these ordered pairs. But when I come to these two ordered pairs right here, 5 is mapped to 6 and 5 is mapped to 8. And for a function, that cannot happen. So this is absolutely not a function here on this first example. And we'll see some things graphically what it means to be a function in just a little bit, but we're just going to start off with ordered pairs. So again, let's talk about our domain and range first. Let's do our x's first. So in this case, I have 1, 3, 6, and 8. Notice they're all distinct, and that's nice. Here I have 2, 4, 5, and 5. 2, 4, and since 5 is repeated, again, I'm not going to write it twice. So now we have to determine, is this a function? Well, I have all unique x values this time, and that is good because each of those unique x values go to a y value. Now you may be looking at these guys right here because they go to the same y value. That is perfectly okay. You can have the same y's, but you can't have the same x's going to different y values. So right here is the problem in this one. So on our second example, that most definitely is a function. Okay? All right, very good. Now, When working with functions, sometimes there's a rule that models the relation. So there's special notation that's used to represent a function, and that is this notation, f of x, okay? Now, I'm going to say is the same as y. Okay, I don't want to write f of x equals y, because sometimes that gets confusing. But if we think about our equations that we looked at earlier, there was things like this, and we were graphing those. We were putting in domain points and getting out a y value and plotting out the points. So what we're basically going to do is replace this now with f of x, okay? So it's kind of like the same thing. Y is the output, f of x is the output. It's just a different notation. So here's a couple examples of functions. I have f of x equals 2x plus 3. I could have f of x equals 10. That's a function. Y equals 10. That's a horizontal line, actually. I could also have things like f of x equals x squared minus 2x plus 1. Those are all functions and different types of functions, but they are all functions. So get used to seeing that f of x because we'll be using that quite a bit. Now, once one has a rule, for instance, this rule is to times the x value by 2 and then add 3, and some values in the domain, which we can also think of are our input values. Again, these are our x's. Then one can determine the range, which is the output value, or, don't forget, those are our y values that match with each relation, okay? All right, so here's a function. It's a quadratic function because I have an x squared, and we're going to just do a couple problems here on how to evaluate each of the following. So remember, this is an x value, and for this first problem, I'm saying, okay, I'm going to let x equal -5. What is that function f evaluated at -5? So basically that means I'm going to plug in -5 wherever I see an x. So here we go. F of -5 is equal to, my rule says to square that number, then subtract twice of that number, and then add 7. So now here's a bunch of order of operations that we have to worry about. So obviously I have a square, so I'm going to take care of that first. -5 squared is 25. -2, well, we could rewrite this, but the next thing that's going to happen is this multiply. -2 times a -5 is a +10, and then I'm going to add 7. So I'm going to run that through as 25 plus 10 plus 7, which gives me 42. Therefore, f of -5 equals 42. Now, if I wanted to plot that point would be the point -5, 42. This is a y value, this is my x value, my input and my output, okay? Now, what if I have something that looks like this? Well, instead of a number, now I have an expression. The idea is exactly the same. Whatever is inside here, I'm going to throw into wherever I see an x value in my function. We're going to evaluate at x plus 4 is what we say in that sense. So I have f of x plus 4. Again, I'm going to go right back in here, take out that x, and put in what's inside my parentheses. So I'm going to evaluate at x plus 4. So x plus 4 goes in here squared, minus 2 times what's inside there. So I'm going to do minus 2 times that x plus 4, and then we can't forget about our plus 7 at the end. Okay, so here is just a whole bunch of mess that we have to clean up, okay? So we still have to, by order of operations, figure this out. Well, in this case, I have to square this, okay? So if you need to write that out twice and FOIL, then please do so. That's going to be my first term, which is x squared. Outside becomes a plus 4x. Inside is a plus 4x. And my last term is a plus 16. So that's just of that x plus 2 or x plus 4 quantity squared. Then I have this -2 that I have to distribute through. So -2 times x is minus 2x. -2 times a positive 4 is a minus 8. And then don't forget about that plus 7. Okay? So this one's actually a little bit harder than the next problem, so we're doing the harder problem first. All right, and then at this point, all we have to do is combine like terms. Okay, your answer is not going to be a number just like it is over here. It is going to be in terms of x. So this is the only x squared I have, so I'm going to rewrite that. Here are all my x terms that I need to put together. So 4 plus 4 is 8, minus 2 gives me a plus 6x. And then plus 16 minus 8 plus 7. So 16 minus 8 is 8 plus 7 gives me a 15. Therefore, f of x plus 4 is equal to x squared plus 6x plus 15. And that would be your final answer. Okay, so again, don't panic that you just don't get a number. That's okay. We will get things in terms of x sometimes, just like what we're going to do here. Again, I'm just going to rewrite that f of x function over here. X squared minus 2x plus 7, since I've written all over the other one. Okay, so now this problem is asking me to take this negative x and throw it in for x, take that negative x and throw it out. So we're going to end up get rid of that, throw in what's inside the set of parentheses, into there. I'm going to get rid of that and throw in what's inside my function notation for what I'm evaluating. And then we have our plus 7. So again, this one's a lot easier. I don't have that expression that I have to square. But negative x times negative x is going to be a positive x squared. Negative 2 times a negative x is a positive 2x. And then I have plus 7. So it looks very, very similar to the original, but this would be our final answer. Okay? All right, very good. So that's evaluating functions, different expressions, and you'll get to practice some of those on your homework. Now, what we're going to evolve into is being able to graph some of these, and we're going to, again, hopefully eventually get away from our t-charts that we had. And so we're still going to do them by t-charts, but we're going to start looking at some patterns here very, very quickly. So we're going to graph the given functions f and g in the same rectangular coordinate system, which is this guy right here, that same coordinate plane. Select integers for x starting with -2 and ending with 2. So we need to know what our integers are. Those were our positive and negative whole numbers. So we're going to start at -2. Let's just do our first one, -2. My next integer would be -1. Then my next one would be 0, 1, and 2. And that's where it's telling me to stop. And it says, once you've obtained your graphs, describe how the graph G is related to the graph of F. Okay, so we're going to start with F here. And we're going to throw in -2 into our function f. Here's our f and here's our g. So the rule here tells me that it's just equal to the x value. So I want to have -2. Throw that in. I get -1. Throw that in. I get 0. Throw that in for x. We get 1 and 2. So let's graph those points. -2, -2 is this guy. -1, -1 is this guy. Here is my 0, 0. Then I'm going to go over 1, up 1 for my 1, 1, and over 2 and up 2 for 2, 2. And I'm going to end up connecting those as best I can. And that is my f function. So sometimes we put a little f at the end there. Now I'm going to come back in a different color and evaluate the g function that we have here. And for g, which is this guy right here, again, we're going to start at -2 and end at +2. So I need -2, -1, 0, 1, and 2. And I'm going to plug this number into this function and add 3. That's the rule that g is telling us to do. Take your number x and add 3 to it. So -2 plus 3 is 1. -1 plus 3 is 2. Throw in 0, add 3 gives me 3. Throw in 1, add 3 gives me 4. And throw in 2, add 3 gives me 5. So these are the numbers that I need to plot now, or the points. So I'm going to go over 2 and up 1 for -2, 1. Then we're going to go from the origin -1 up 2. Then we're going to go up 3 on the y-axis, nothing in the x direction. Over 1 and up 4. And over 2 and up 5. All right. So there's our points that I'm going to now connect, hopefully, somewhat. Okay, so that's our g function. Now the last thing that it asked me to do is to compare the two. What happened to the f function to get to the g function? Well, if you notice, everything corresponding points moved up 1, 2, 3. So what we did, we went up 3, or a vertical shift by 3. Oops, sorry. Okay, that's what we did to describe g and related to f. Okay, all right, let's try this f function. Let's do by a t-chart and start with -2, -1, 0, 1, and 2. And again, we're going to throw that in to our our f function. And this time the rule says me to take my number and square it. So -2 squared is a 4, -1 squared is a 1, 0 squared is 0, 1 squared is 1, and 2 squared is 4. So let's plot those points on our graph. Here's -2, 4. Here's -1, 1, 0, 0. Over 1 up 1 gives me 1, 1. And from my origin over 2 and up 4 gives me that. If you recall in section 1.1, we did see some of these. These are what we refer to as parabolas. They are kind of a U shape. Anytime you have an x squared, you're going to have that U shape. All right, so let's change our color here. This was for F. Let's now try for G. -2, -1, 0, 1, and 2. And now our rule for G, if we look at that, tells us to square our number and then subtract 4. So exactly what we just did, but we're going to square it and then subtract 4. So I'm going to square this. -2 squared is 4, minus 4 is a 0. If I throw 1 in, -1 squared is positive 1, 1 minus 4 is -3. If I throw 0 in, 0 squared is 0, minus 4 is -4. If I throw 1 in there, 1 squared is 1, minus 4 is -3. And 2 squared in there is 4, minus 4 gives me a 0. So now I'm going to plot these points, and then we have to describe what happens to this graph. So here's -2, 0. From the origin, -1 down 3 gives me -1, -3. Nowhere on the x-axis, but down to 4 for 0, -4. Then we're going to go over 1 and down 3. Then we're going to go over 2 and nowhere in the y direction, okay? So we're going to now connect those points. And then we describe what happened to the red parabola to get the blue parabola. What did we do? Well, notice that if this is my origin now, or excuse me, at the origin, then I've moved it down here as kind of the turnaround point or that minimum point, okay? So here is that, and so we are going to end up describing that as being a vertical shift down by 4. So it went down 4. Okay, now hopefully you can kind of recognize in my equation, this was a -4 and this was a +3, and that was kind of an indicator of this going up by 3 for my first one and this going down by 4. There is a correlation there, okay? All right, let's see if we can try a couple more. All right, this one being an absolute value. Same idea. Hopefully maybe we could see what's going to happen here. X, Y, so this is going to be for F. -2, -1, 0, 1, and 2. A lot of pattern work going here. Remember, the absolute value is the distance from 0. So when I throw in -2, take the absolute value, we get a +2. Throw in -1, we get a +1. 0 is still 0. The positives stay exactly the same. So plotting those 2 points, or excuse me, those 5 ordered pairs, -1, 1, 0, 0, 1, 1, and 2, 2. So an absolute value, if you recall from earlier in chapter 1, it is a V shape. So you have to have that forming there. If not, then you've done something wrong. All right, let's check out our G function. And we're going to do -2, -1, 0, 1, and 2 again. When I throw that into here for g, take the absolute value is 2, minus 1 is 1. Throw in -1, absolute value -1 is 1, minus 1 is 0. Throw in 0, absolute value is 0, minus 1 is -1. Put in 1, we should see a pattern where we get the same answer as this one. And when I throw 2 in there, we're going to get the same answer as that one. And so now when I plot these points, -2, 1, -1, 0, 0, -1, 1, 0, and 2, 1. Now here is my V shape. And what happened to the F function to get to the G function? We moved everything down by 1. Now look what was at the end of that. We had it down by 1. All right, now this one's a little bit different just because I wanted to show you one of these because it is a special function. I alluded to it earlier when I wrote you some examples of those. We're going to still do -2, -1, 0, 1, and 2. But this time, f of x equals 2. There's no x value in there. It's not going to change. So I don't care what number I put in here for x, the output value will always equal 2. Everything gets a 2. There's no changing it. It is constant. So when I plot those points, -2, 2, -1, 2, 0, 2, 1, 2, and 2, 2. Hopefully you recognize that as one of our horizontal lines. If I wrote that as y equals 2, we saw those before. So it's very important for you to remember and be able to recognize that those are actually going to be horizontal lines. All right, so just keeping with our process here, -2, -1, 0, 1, and 2. This time we're putting into the g function, but over here there's no x value. It is always equal to -4. There's no x for it to change. Therefore, no matter what x value that I throw in there, I'm going to get a y value of -4. So plotting those points, -2, -4, -1, -4, 0, -4, 1, -4, and 2, -4. Here gives me this nice horizontal line again. Now, we still have to determine what happens from F to get to G. And in this case, we took our entire horizontal line and we moved it down a distance of 1, 2, 3, 4, 5, 6. So here we went down by 6. Okay? All right, very good. Hopefully there's not many questions on that. So, these are all actual functions. I did f of x, g of x, we could do h of x. The letter doesn't matter, just that you have that notation, which is kind of funny to get used to at first. But not all relations are functions. And if I see a graph of a function, it's going to be nice and easy to determine whether or not a relation is a function. And that is by testing it. And more specifically, we're going to use the vertical line test to determine if a relation is a function. And so the vertical line test says this: if any vertical line intersects the graph in more than one place or one point, then the relation or the graph is not a function. It can only intersect a vertical line in exactly one place for it to be a function. So, using the vertical line test, can we determine if this graph is a function of y in terms of x? So if I check any vertical line that I would draw through that function, how many places does it intersect? 1, 1, 1, 1, 1. So yes, this would be considered a function. If I draw a vertical line right there, now it looks kind of like a dollar sign. I intersect that function in 1, 2, 3 places. Therefore, that is not a function. If I look at part C and I start drawing all kinds of vertical lines, no matter where I draw that vertical line, as it keeps going and going and going, it only intersects it in one spot. So yes, it is a function. And then we have a circle here. Is a function, is a circle defined to be a function? And notice right here and right here, there are 2 spots that it crosses. Therefore, it is not going to be a function. So that's a nice easy test, but sometimes we forget about it. So make sure that you remember that and put that in your toolbox. All right, so another exercise is going to be able to use this graph that I have here to answer some of these questions. This is the graph of f, okay? And I'm asking to evaluate f of -2. Remember, this is asking me for a y value when x equals -2. And so if I look at my graph, here are my x's along here, and here's where -2 is. There's my point. If I want to put the ordered pair on that point, that would be the point -2, 0. And what is the f of -2? Well, what's the y value when x equals -2? It is 0. So we found this using a function earlier with a rule, but now it's using a graph. If I look at f of -1, what is f of -1? Looking on there, there's my point. And if I want to do an ordered pair, it would be the point -1, 6. Therefore, if I want to find f of -1, in this case, it would equal 6. Okay? Now, we're going backwards. We need to now find the x values that make this true for our function. We're looking for the x's in which our y value is equal to 4. So here's our y. Well, where's 4? 4 is right here. I'm going to undo that, and I'm going to do like a dotted line there along y equaling 4, because there's actually more than one answer here. Because if I look along this horizontal line and I say, okay, where in the world is this going to be crossing my function? I've got this point, and that point. And so there's actually 3 x values that make that true. Well, what x value is that? Well, here's one. I'm going to call that like a -1.5. I know we don't know for sure exactly, but if I look at this guy, I also am kind of partly through. This one's the only one that's nice when x equals 0. So I'm going to say what value of x, well, there's actually multiple values. 0 is 1. I'm going to go -1.5 is 1. And then this value here in between 2 and 3, I'm going to approximate that as 2.5. So make sure that you're able to decipher between the different ways that they ask that. Okay? All right, very good. Now, we are going to look at determining multiple pieces or characteristics about a function just by giving its graph, okay? So, use the following graphs to determine A, the function's domain, B, the function's range, C, the x-intercepts, which is where they cross the x-axis, the y-intercept where it crosses the y-axis, if there are any, and the missing function values indicated below the graph. So it means these guys right here. Okay? So let's start with A. A, we did domain earlier with points. Now we're going to do it with a graph. Now, if we have a function, and hopefully you recognize that somewhat as an absolute value function because it is in V shape, we need to determine the domain. Now, graphically, you're going to look left to right and determine what values do I take out. Well, notice this arrow and this arrow. This means this keeps going on forever and ever and ever and ever and ever. If I want an x value over here, I can find the y value up there. If I want an x value over here, there's a matching y value up there. So when you have these arrows that are kind of going left to right, that is symbolizing that we have an all real numbers domain. There's not an x value that I can't find a point on. So you can write it like that with a funky little r, or if you remember with interval notation, we can do that from -infinity to +infinity. Okay? Now, the domain, or excuse me, the range is a little bit different. The range now, we are looking at what values in the y direction do we have. So for instance here, there's nothing on my function down here. Now we're looking vertically, kind of and up and down. So if I start here, that's the bottom out point. That's the minimum of my function. So now I'm going to have to go for everything above that. Well, what is the y value here? -1. It is at 0. So our range, we can include 0 because there's a point there. So I'm going to do a bracket, and I'm going to go from 0 to infinity. Okay? So this is basically saying everything greater than or equal to 0. All right, then part C, we want to find the x-intercept. So we're going to look along here and see where our point is that intersects the x-axis. And that is right there at -1. Therefore, that is my x-intercept. When I look at the y-axis, and I'm looking for where that function crosses or intersects, and it is right there, which is at +1. And our last part here, section E, says that we need to find out what these values are on our function. Now remember, it's just looking for the y value when x equals -4. It's just looking for the x value, or excuse me, the y value when x equals +3. So let's go over on our graph at -4, and I'm going to go and look at this point. That is the point -4, 3. Therefore, when I throw in -4, 3 is going to kick out. Therefore, f of -4 is 3. And if I go over to +3, and I look at that point right there, that is the point 3, 4. Therefore, when I throw in 3 into my function, what kicks out? It is a 4. Therefore, f of -4 is 3, and f of 3 is equal to 4. Okay, so let's practice that for 2 more on the next page, and then we'll be out of section 2-1. All right, part A, we're looking for our domain. So I'm looking here left to right. Notice there's nothing over in here on my function. It starts right here at -1. And everything beyond that will have a value, because remember, that keeps going and going and going. Therefore, from -1 to infinity, we have our domain. Those are my allowable x values. Okay, so we're going to include -1 to infinity. Now part B, look from down to up. Go from the bottommost point and keep going up. Well, notice here, nothing up here until I get to 0, and then I have everything accounted for. Even if I have this one, there's going to be something way out here on that function. Okay, so I know that's kind of abstract in a sense, but we're going to start at y equaling 0 to infinity. Okay. C are our x-intercepts. So I look across the x-axis, and I'm intercepting right here at -1. These should be easy. Along the y-axis, where do we cross? It is at +1. Therefore, that's my y-intercept. And I need to now look at what is f of 3. So I go to my function, and I find the point on that function where x equals 3. That is the point 3, 2. So when I throw in 3, what kicks out? It is the y value of 2. And that gives us our 5 parts that we're looking for. All right, last one for section 2-1, and then it'll be your time to try. So we're looking for our domain left to right on our x's, and notice nothing until I get to -6. But this open circle tells me I'm not including that. So the way I do that with interval notation is to do that parenthesis. Now I keep going on my function, and it stops right here. So what x value does it stop at? It goes from -6 to 0. Now that's a solid dot, so I'm including 0. Therefore, -6 to 0 would be my domain. If I then look up and down for my range is going to be the y values. So I'm going to start from the bottom and move up. Well, notice my function here includes -3. So I'm going to do that with a bracket. And I keep going up, 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 up. And my y values stop up here at the y value of 4. So we're going to, now remember it's an open circle here, so we're not going to include 4 with a parenthesis. Okay. All right, part C are our x-intercepts along the x-axis. Where do we cross? It's right there at -4. And on our y-axis, where do we cross? It's right there at -3. Therefore, those are my x and y intercepts. And our last thing is to determine what is f of -4. If I look at f of -4, here's -4. That is the point -4, 0. So when I throw in -4, what's the output? It is at 0, and that's the function value when x equals -4. Okay? All right, very good. Well, that's our beginning of section, actually chapter 2, which is going to get us some more graphing here in some subsequent sections. So hopefully you master this first so we can move on later. Until next time.